Download this code from codegive.com, link in the description below. A cache of pedantic corrections, building robust and debuggable code with static analysis and custom linting. This tutorial explores the concept of proactively identifying and correcting potential issues in your code base through the use of static analysis and custom linting rules. We'll call this proactive process a cache of pedantic corrections, CPC. The goal is to catch issues before runtime, improving code quality, reducing bugs, and promoting maintainability. This goes beyond simple style enforcement. We're aiming to enforce deeper semantic correctness and best practices. What is a cache of pedantic corrections? Imagine a cache filled with meticulously crafted rules and checks that examine your code for potential pitfalls. This cache acts as a proactive guardian, identifying subtle errors, stylistic inconsistencies, performance bottlenecks, or violations of project-specific standards before you even run your code. Think of it as a highly critical, pedantic code reviewer available 24/7. This isn't about nitpicking spacing, it's about preventing real bugs and improving code clarity. Why use a CPC? Early bug detection catches errors during development, saving time and frustration later in the development cycle. Identifying issues early is always cheaper than finding them in production. Improved code quality enforces coding standards, promotes best practices, and reduces code complexity. Enhanced maintainability consistent code is easier to understand, modify, and debug. A well-maintained CPC helps new developers quickly grasp project-specific conventions. Reduced technical debt prevents the accumulation of quick fixes and workarounds that can lead to future problems. Team consistency ensures that all developers are adhering to the same coding standards, promoting collaboration and reducing code review friction. Customizable to your project you can tailor the CPC to the specific needs and requirements of your project, addressing domain-specific issues. Documenting best practices the rules themselves serve as documentation, educating developers on common pitfalls and best practices within the project. Tools of the trade, static analysis and linting. The key to building a CPC is leveraging static analysis and linting tools. These tools examine your code without executing it, identifying potential issues based on predefined or custom rules. Linters primarily focus on code style, formatting, and basic code quality. Examples include JavaScript /TypeScript ESLint, JS hint, prettier. Python Pylint, Flake 8, black. Java check style, PMD, find bugs, now spot bugs. C/C++ clang tidy, check. Go Golang lint. Static analysis tools go beyond stylistic checks and perform deeper analysis to identify potential bugs, security vulnerabilities, and performance issues. Examples include JavaScript /TypeScript SonarCube, semgrep. Python SonarCube, bandit, security focused. Java SonarCube, find bugs /spot bugs. C/C++ Coverighty, SonarCube. Go SonarCube, static check. Building your CPC, a step-by-step guide. Here's a comprehensive guide to building your own cache of pedantic corrections, focusing on the practical aspects and providing code examples. We'll use ESLint, for JavaScript /TypeScript, as a primary example, but the principles can be adapted to other languages and tools. 1. Project setup, example, JavaScript/TypeScript with ESLint. Asterisk install node.js and npm, or yarn/pnpm. Asterisk create a new project directory asterisk. Asterisk install ESLint and TypeScript, if applicable. Asterisk initialize ESLint asterisk. Follow the prompts to configure ESLint for your project. A common setup is asterisk to check syntax, find problems, and enforce code style. Asterisk JavaScript modules, import/export. Asterisk React, if applicable, or none of these. Asterisk does your project use TypeScript? Yes, if applicable. Asterisk where does your code run? Browser and /or node. Asterisk what format do you want your config file to be in? JavaScript, or YAML or JSON. This will create an .slintric.js, or .slintric.yaml or .slintric.json file in your project root. 2. Configuring ESLint, the core of your CPC. The .slintric.js file is where you define the rules that make up your cache of pedantic corrections. Asterisk extending existing configurations. Asterisk start by extending a well-established configuration to avoid reinventing the wheel. Popular options include asterisk ESLint recommended, ESLint's built-in recommended rules. Asterisk plugin at TypeScript ESLint/recommended, recommended rules for TypeScript. Asterisk Airbnb base, Airbnb's JavaScript style guide, a good starting point for style enforcement. Asterisk Google, Google's JavaScript style guide. Asterisk customizing rules. Asterisk override the settings of inherited rules or add new rules to fit your project's specific requirements. ESLint rules have 3 severity levels. Asterisk off or 0, disables the rule. Asterisk warn or 1, reports the rule violation as a warning. Asterisk error or 2, reports the rule violation as an error, typically causing the build to fail. Here are some examples of common rule customizations. 3. Advanced CPC, creating custom ESLint rules. The real power of a CPC comes from creating custom rules that address your project's unique needs and coding patterns. Asterisk rule structure. Asterisk a custom ESLint rule is a JavaScript module that exports a single object with the following properties. Asterisk meta, describes the rule, documentation, fixable status, message placeholders. Asterisk create, context, a function that returns an object containing visitor functions. These visitor functions are called when ESLint encounters specific nodes in the abstract syntax tree, AST, of your code. Asterisk example, a rule to prevent magic numbers, literals directly in code. Let's create a rule that discourages the use of magic numbers, numeric literals used directly in code without explanation. This improves readability and maintainability. 1. Create a rules directory asterisk in your project root, create a directory named rules. 2. Create a rule file, rules/nomagicnumbers.js. 3. Update .slintric.js to include the custom rule asterisk. Explanation asterisk. Asterisk meta, defines the rule's metadata, including its type, description, recommended usage, and a message ID. The schema allows you to define options for the rule. Asterisk create, context, this function is the heart of the rule. It receives a context object that provides information about the code being analyzed. Asterisk literal, node, this is a visitor function that's called whenever ESLint encounters a literal node, example 123, hello. We check if the literal is a number and, if so, report an error using context.report. Asterisk message ID, references the corresponding key in the messages object of the meta object. Asterisk writing more complex rules. Asterisk you can access various properties of the AST node through the node object. You can also use the context object to access the source code and report errors. Refer to the ES-tree specification, https://github.com/estree/estree, for details on the AST node structure. 4. Running the linter. Add a script to package.json run the linter ESLint will now analyze your code and report any violations of the configured rules, including your custom rules. 5. Integrating with your workflow. Pre-commit hooks, Husky, lint staged run the linter before each commit to prevent code with violations from being committed to the repository. CI/CD pipelines integrate the linter into your CI/CD pipeline to ensure that all code meets the required standards before deployment. Editor integration. Install ESLint plugins for your code editor, VS Code, Sublime Text, etc., to get real-time feedback as you type. Code examples, illustrative. Here are some code examples demonstrating how the CPC would flag certain issues. Beyond ESLint, expanding your CPC. While ESLint is a powerful tool, it's just one piece of the puzzle. Consider incorporating other static analysis tools into your CPC. TypeScript compiler, TSC leverage TypeScript's type checking capabilities to catch type-related errors early. Configured config.json with strict options, strict, true. SonarCube a comprehensive static analysis platform that supports multiple languages and provides detailed reports on code quality, security vulnerabilities, and maintainability issues. SemGrep a fast and flexible static analysis tool that allows you to define custom rules using a simple, declarative syntax. It's excellent for security-focused checks and identifying code patterns. Code Climate a hosted service that performs static analysis and provides insights into code quality. Best practices for building a successful CPC. Start small and iterate. Don't try to implement everything at once. Start with a small set of core rules and gradually add more as you gain experience. Prioritize rules. Focus on the rules that are most likely to prevent bugs and improve code quality in your specific project. Involve the team. Get buy-in from the entire team and involve them in the process of defining and refining the rules. Automate the process. Integrate the linter into your build process and use pre-commit hooks to enforce the rules automatically. Document the rules. Clearly document the purpose of each rule and why it's important. This will help developers understand the rules and avoid violating them. Regularly review and update. Review and update the rules regularly to reflect changes in the project's requirements and coding practices. Balance pedantry with pragmatism. Don't be overly strict. The goal is to improve code quality, not to stifle creativity or slow down development. Sometimes, exceptions are necessary. Make them explicit and documented. Measure and track. Track the number of violations detected by the linter over time. This will help you assess the effectiveness of your CPC and identify areas where you can improve. Conclusion. Building a cache of pedantic corrections is an investment that pays off in the long run. By proactively identifying and correcting potential issues in your code base, you can improve code quality, reduce bugs, enhance maintainability, and foster a culture of excellence within your development team. Embrace the power of static analysis and custom linting rules to create a more robust, reliable, and enjoyable development experience. Remember to tailor your CPC to the specific needs of your project and continuously refine it as your project evolves. A cache of pedantic corrections, a deep dive into memoization with Python. This tutorial delves into the world of memoization, a powerful optimization technique often used to improve the performance of recursive functions and computationally expensive operations. We'll go beyond the basics and explore how to create a robust, cache-based solution that addresses potential pedantic corrections, subtle edge cases and considerations often overlooked in simpler implementations. We'll be using Python for our examples, taking advantage of its built-in functools.ru_cache decorator and then building our own custom solution for more fine-grained control. What is memoization? At its core, memoization is about caching the results of function calls and reusing them when the same inputs are encountered again. Think of it like a cheat sheet you keep handy. Instead of resolving a problem you've already tackled, you simply look up the answer. Why use memoization? Performance boost. Significant speed up for functions with overlapping subproblems, example Fibonacci sequence, dynamic programming problems. Reduced computational load. Avoids redundant calculations, freeing up resources. Improved user experience. Faster response times for interactive applications. The classic example, Fibonacci sequence. Let's start with the canonical example, calculating the nth Fibonacci number. The naive recursive implementation is notoriously inefficient. This code exhibits exponential time complexity because it repeatedly calculates the same Fibonacci numbers. Fibonacci, 5, calls Fibonacci, 4, and Fibonacci, 3. Fibonacci, 4, then calls Fibonacci, 3, and Fibonacci, 2, and so on. The problem is that Fibonacci, 3, is being calculated twice in the first step. 1. Memoization with functools.ru_cache, the quick and easy way. Python's functools module provides a convenient decorator, ru_cache, for automatic memoization using a least recently used, LRU, cache. Explanation **** at functools.ru_cache, maxsize equals none, this decorator wraps the Fibonacci_memoized function, creating a cache. Maxsize equals none, specifies that the cache can grow without bounds, until memory runs out. If you specify a number, it will hold only the most recently used items, evicting older ones when the limit is reached. This is helpful for controlling memory usage. How it works. When Fibonacci_memoized, n, is called, ru_cache first checks if the result for n is already in the cache. If it is, the cached value is returned immediately. If not, the function is executed, the result is stored in the cache, and then returned. Fibonacci_memoized.cache_info, provides statistics about the cache, hits, misses, maxsize, and current size. This is useful for debugging and understanding how effective the cache is. Advantages of ru_cache ***. Simplicity ***, easy to use with just a decorator. Built-in ***, no need to write your own caching logic. LRU eviction ** automatically manages the cache size by discarding the least recently used entries when the cache is full. Limitations of ru_cache ***. Immutability requirement ***. The function's arguments must be hashable, immutable, objects. This means you can't directly memoize functions that take lists or dictionaries as arguments, unless you create hashable representations, like tuples of sorted items. Asterisk limited control. Asterisk you have limited control over the cache eviction policy beyond the LRU algorithm. Asterisk no custom key generation. Asterisk the function's arguments are used directly as the cache key. Sometimes, you might want to derive a more specific key based on the argument's content rather than their identity. Asterisk no persistence. Asterisk the cache is in memory and lost when the program terminates. 2. Building a custom memoization decorator, for pedantic control. To overcome the limitations of LRU_cache, let's create a custom memoization decorator that gives us more control. This will allow us to address potential pedantic corrections related to argument handling, cache eviction, and key generation. Explanation. Asterisk 1. Memoize class. Asterisk the main decorator class. It takes the function to be memoized, func, as an argument, along with optional parameters. Asterisk key_function, a function that takes the same arguments as the memoized function and returns a hashable key. If not provided, the default key function is used. Asterisk maxize, the maximum number of entries to store in the cache. If none, the cache grows indefinitely. Asterisk persist_to_file, optional file name to persist the cache to disk. 2. __init___ method. Asterisk initializes the cache, self.cache, stores the function and key function, and loads the cache from file if applicable. 3. __call___ method. Asterisk this makes the memoize object callable, i.e., it acts like a function. It's the heart of the decorator. Asterisk calls the key_function to generate a cache key based on the input arguments. Asterisk checks if the key exists in the self.cache. If so, returns the cached value, a cache hit. Asterisk if the key is not in the cache, a cache miss, it executes the original function, self.func, stores the result in the self.cache, enforces the maximum size, persists to file, and returns the result. 4. _default_key method. Asterisk provides a default key generation function that converts arguments to tuples and frozen sets to handle unhashable types. This addresses a common pedantic correction. LRU_cache requires arguments to be hashable, but not all arguments are, example lists, dictionaries. Asterisk by converting to tuples and frozen sets, we create hashable representations of the arguments. This allows us to memoize functions that take lists or dictionaries as arguments, based on their contents. Asterisk important. Asterisk the order of items in lists and dictionaries matters for this default key. 5. _enforce_maxize method. Asterisk implements a basic FIFO, first in, first out, cache eviction policy. If the cache exceeds maxize, it removes the oldest entry. This is a very simple eviction strategy. 6. Cache_info method. Asterisk returns a dictionary containing cache statistics, hits, misses, maxize, current size, similar to LRU_cache.cache_info. 7. Save_cache_to_file and load_cache_from_file methods. Asterisk implement persistence to disk using pickle. This allows the cache to be saved between program runs, which can drastically improve performance if the same calculations are repeated across multiple invocations of the program. Example usage. Asterisk addressing pedantic corrections, key customization and argument handling. The key_function argument to our memoized decorator is crucial for handling potentially tricky cases where the default key generation isn't sufficient. Here are some scenarios. Asterisk ignoring irrelevant arguments. Asterisk suppose your function takes an argument that doesn't affect the result. Including it in the cache key would lead to unnecessary cache misses. Asterisk normalizing arguments. Asterisk sometimes, arguments might have different representations that are logically equivalent. For example, you might want to treat apple and apple as the same key. Asterisk complex data structures. Asterisk for more complex data structures like dictionaries or objects, you might need to create a key that represents the relevant parts of the structure. You might hash the relevant attributes of an object, or create a canonical string representation of a dictionary. Example with cache persistence. Important considerations. Asterisk cache invalidation. Memoization can become problematic if the underlying data or dependencies change. You might need mechanisms to invalidate the cache when the data is updated. This is where the ru_cache.cache_clear method or custom cache management strategies become important. Our custom memoize class doesn't have a cache_clear method, but it's easily added. You could also add an expiration time to cache entries. Memory usage. An unbounded cache can consume a significant amount of memory, especially for functions with a large input space. Carefully consider the maximize parameter and choose an appropriate cache eviction policy. Thread safety. The ru_cache decorator is thread safe in Python 3. However, our custom memoize class is not thread safe without additional synchronization mechanisms, example using threading.lock. If you are using it in a multi-threaded environment, you will need to add appropriate locking. Side effects. Memoization should only be used for pure functions that have no side effects and always return the same output for the same input. If a function modifies external state, caching the result can lead to unexpected behavior. Going further, advanced techniques. Cache eviction policies. Explore more sophisticated cache eviction policies beyond FIFO, example least recently used, LRU, least frequently used, LFU, time to live, TTL, based eviction. Cache backends. Instead of an in-memory dictionary, use a more persistent cache backend like Redis or MEMC for distributed caching and larger data sets. Key serialization. Consider using more robust serialization methods, like JSON or protobuf, for complex data structures when saving the cache to disk. This can improve compatibility and performance. Function composition. Combine memoization with other functional programming techniques like partial application and currying for highly optimized and reusable code. Conclusion. Memoization is a powerful tool for optimizing computationally intensive functions, particularly those with overlapping subproblems. While functools.ru_cache offers a quick and easy solution, a custom memoization decorator provides greater flexibility and control to address potential pedantic corrections related to argument handling, key generation, and cache management. By carefully considering the trade-offs and potential pitfalls, you can leverage memoization to significantly improve the performance of your Python code. Remember to always analyze the specific requirements of your application and choose the approach that best suits your needs.